Okay, so this is the second of the 4 lectures on arithmetic and Gödel's incompleteness theorems. So last week we did what is that? Might need another trip downstairs. Okay, that'll do. And last week, the important concepts where we had the language of arithmetic, which is the signature that we use to express properties of number theory. That was a very simple signature where we had 0 and addition, multiplication, and a unary successor operation on the natural numbers. And using so this is the signature of arithmetic, which we call LA for the language of arithmetic. Using the successor operation, we define the numeral n overline for every natural number n. So for example, it's just the representation of the number. So 3 is successor applied 3 times to 0. So with the so-called delta 0 formulas, are bounded. So we defined the order relation, and quantifiers have to have specified upper bounds for the delta. A is delta 0. One way in which we used the notion of sigma 1 formula was we showed that we could represent the exponentiation function, x to the power of y, using an arithmetic formula, actually represent the ternary, that's the 3-argument relation z equals x to the power of y, and we could represent that using a sigma 1 formula. So we had exponentiation is sigma 1 representative. And even going back to the early lectures on the course, I gave examples of interesting properties in number theory that can be expressed in this first order language. So this is called the language of arithmetic, and one can use it to express interesting properties of number theory. So from the language, we have properties we can express, and essentially all we've got is the first order language with these very simple building blocks for terms. So all formulas with quantifiers, all the quantification, we interpret it as being over the natural numbers. So we have things like there are infinitely many primes. For every number, there exists a larger number such that that larger number is prime. And obviously we can iterate the quantifiers a bit more than that, but still we only have iterations of first order quantifiers over the natural numbers, and doesn't require that much imagination to believe that those kinds of sentences formed in this way have a definite truth value. We might not know what it is, but still the infinite collection of natural numbers, it may be infinite, but it's still infinite in a very simple way, and we can imagine that any first order sentence in this language does indeed have a definite truth value. And one of the goals of number theory is to explore properties of numbers. Many of them can be expressed in this language, and we're trying to ascertain which sentences if we've got an interesting property, we want to know, is it true or not? So we're interested in the theory of what's called true arithmetic. So again, this seems to be not a black pen day again. Let's try another one. Interested in the theory of true arithmetic. So that's the theory of, well, what, strictly speaking, we last week called curly n, which is the same as the theory of the curly n with the natural numbers with the standard interpretations of zero, addition, multiplication, and successor. I will just normally write the theory of natural numbers. Okay, so that's theory of mathematical interest. And the big tool we have from logic for understanding theories, one of the big tools is axiomatizations, because axiomatizations allow us to prove theorems, and indeed many theorems of numbers going back to the ancient Greeks and Euclid, proving properties like there are infinitely many primes, are essentially proved axiomatically from, well, I mean, nowadays one would write those proofs axiomatically from simple axioms about the natural numbers. So what we want is to it'd be a nice goal is to axiomatize this theory. And Gödel's first incompleteness theorem will tell us that we can't actually achieve this goal, in the sense that whatever good computable axiomatization we have, we're inevitably going to not capture all the truths of natural numbers. Nonetheless, we can come up with very reasonable axiomatizations for the natural numbers. So we're going to start with the most famous such reasonable axiomatization, and that's the theory known as Peano Arithmetic. Okay, so we're going to consider the standard first order axioms for arithmetic. After Giuseppe Peano, the 19th century Italian mathematician. Okay, so Peano Arithmetic which is normally abbreviated to PA. It's the canonical axiomatization of number theory in the first order language of arithmetic. And it consists of 6 axioms plus 1 axiom schema. And the 6 axioms are all very simple. They're all expressing essentially properties that define the meaning of these symbols. And they're chosen to express just those properties that one really needs. So the first ones concern the successor operation. It's axiomatized that it's injective. So you can axiomatize that like that. Of course, axioms are strictly speaking sentences in this course. So really we mean for all x for all y, but I'm going to adopt the standard practice that one omits outside universal quantifiers. So there are 2 main axioms for successor. The second one is that the successor of anything is never 0. Okay, so we're not allowed to go around in a loop and get back to 0. The third and fourth axioms essentially amount to giving a recursive definition of addition in terms of the successor operation. So we've got for all x, x plus 0 is x. We're going to recursively define addition with the recursion being in the right argument here. So we define x plus 0, and then we need to say also what addition is if we use a successor in the right-hand argument instead of 0. And in that case, well, it's the successor of whatever we get from x plus y. And of course, these axioms are chosen so that you can actually, if you view them as what are called rewrite rules from left to right. If you've got this expression, you rewrite it with the one on the right. And if you've got this expression, you rewrite it with the one on the right. Also, for any substitution instance of that, if you're given any two numerals, m plus n, so you've got two numbers, m and n, and we've got the two numerals for them, just by taking the successors off from the right-hand side one at a time, repeating it n times, you get n applications of this axiom with the transitivity of equality, gives you that you can prove that this sum is what it should be, the numeral for n plus n. And the fifth and sixth axioms do the same thing for multiplication. Again, we'll do the recursion in the right-hand argument. So in case of multiplication, when you have 0 in the right-hand argument, it's 0. And if you have the successor in the right-hand argument, well, this is, I mean, because addition is commutative, there are different, and multiplication too, there are different ways one could write it, but the standard way is to do x times y plus x. I think like writing the axioms this way, for those of you who know about ordinals, I think they are also correct axioms for ordinal addition and multiplication. I should double check that, but hopefully they are. At the moment, it could actually be a theory of ordinals, because the ordinals have a successor that satisfies these properties, and an addition operation and a multiplication operation that, well, hopefully these are the right axioms for that. I think I've really thought about it before. Well, I have thought about it before, but I should have really thought about that before now within the window of my memory at the moment, which is it seems to get narrower every time. Okay, so these are 6 axioms, and then the axiom schema. We have 6 axioms. Plus 1 axiom schema. Remember, an axiom schema is infinitely many axioms where we give a pattern, and any instantiation of the pattern gives us such an axiom. And the axiom schema is induction, the induction principle for natural numbers. If a formula A holds, remember I've used this notation before, this is saying we identify some free, A may have many free variables, but we're identifying some particular free variable Z, and we're substituting 0 for that free variable. So if A in the free variable Z holds for 0, and for all x, if A holds for x, then it holds for the successor of x. Then, for all x, A holds for x. And once again, really there are, A is a formula with Z, which is the variable we're substituting the x for, and some other free variables potentially, not necessarily, but y1 to yk. Oops, that should be yk. And really, there's a for all y1 to yk here as well. But as always, I'm kind of omitting the external quantifier. And it's important that the axiom applies to formulas that have other free variables other than the variable that we're substituting the 0 and the x for. It's vital to have other variables in the formulas. Okay, so it's clear that these axioms are all true, virtually, in the natural numbers. They're all principles of the theory of true arithmetic. And this is a very successful axiomatization. So PA is a successful axiomatization. Of arithmetic, in the sense that it can, well, where success here, I don't mean success with axiomatizing all of true arithmetic, because you know that's not possible, because we've already discussed that. So what I mean here is a practically successful. So it turns out that, I mean, as far as we know, Peano arithmetic can, within Peano arithmetic, you can prove the theorems of number theory that are statable in first order arithmetic. That's known for many things. So obviously, it's easy to do the simple proofs like there are infinitely many primes and so on, but also one can prove complicated results like the prime number theorem that's about the asymptotic density of the prime numbers, that the standard proof for that uses complex analysis, but there's an elementary proof, that elementary in the sense that it doesn't use, that it's just it can be formulated in the language of number theory, first order number theory, and that can be formalized in Peano arithmetic. Many people believe Fermat's last theorem can be formalized, can be proved in Peano arithmetic, though I don't think anyone's shown that. But anyway, in practice, people think of this as a successful axiomatization of arithmetic. However, Gödel's Gödel's incompleteness theorems apply, in particular the first one. However, there are true sentences of arithmetic that have no proof in Peano arithmetic. So this is Gödel's first incompleteness theorem, and the goal of next week's lecture is to prove Gödel's first incompleteness theorem in the way that Gödel first proved it, which is a very nice proof. Today we are actually going to prove this theorem in a different way, which is a much less satisfying proof, but nonetheless it will get us this result. I'll comment later about ways in which it's less satisfying than what Gödel did. So we're already going to get the result that Peano arithmetic is incomplete in today's lecture. So Peano arithmetic is incomplete. So we've got Peano arithmetic, let's put it over here on the right. It's contained in true arithmetic, the true sentences of the natural numbers. So this is a strict inclusion of the sentences in the theory. Because of this, because it's incomplete, you might want to extend it with some ways, add some new principles to be able to prove more things. And that's a very good goal. You can never avoid the essential problem of incompleteness, as we'll see already today. Again, we'll see that you can never avoid incompleteness. But I'm going to leave discussing this goal for the future, so how one can get more powerful theories that allow us to establish more truths of arithmetic. Arithmetic's incomplete. It's also a good question to ask, can we pinpoint exactly where the incompleteness phenomenon comes from? And for doing that, it's actually useful to look at weaker theories than Peano arithmetic, because we're going to find a very weak theory that we can use as a base theory and prove a result that any consistent, computably axiomatizable is necessarily complete. So I should have commented while the axioms were here that the Peano arithmetic is computably axiomatizable. So we had that concept last week, I think. No, 2 weeks ago, we had the concept of computably axiomatizable. So what it means is you can decide if a sentence is an axiom. Well, any finite axiomatization is computable, but this isn't a finite axiomatization, but we've got the finitely many axioms, so we can decide if a sentence is one of those. And then we've got this induction schema, and this induction schema has a clear pattern. And if you want to decide, is a sentence an instance of the induction schema, you just parse the sentence and have a look. Does it have this? It should have these quantifiers in, but does it have explicitly this form? So it's a simple computational task to decide if something is an axiom. So this is computably axiomatizable. And the minimum theory is called Q for some reason. I don't actually know why. It was proposed by one of the Robinsons, but it's not, I think, Raphael Robinson. So it's the Robinson that did arithmetic. That's Abraham that did non-standard analysis that we talked about a few weeks ago. That's Abraham Robinson. There's Julia Robinson and Raphael Robinson in logic from all around the same time. I think this was Raphael Robinson. Anyway, the theory Q is actually a finitely axiomatizable theory. So Q is the theory that we get by taking, again, the same 6 axioms that we started with Peano arithmetic, the ones talking about the successor, the addition and multiplication, and we add to that what I call AQ, the axiom for Q, where AQ is the sentence for all x, either x is 0 or there exists a y such that x is the successor of y. So this is clearly a true principle of number theory. We didn't put it in Peano arithmetic. Why don't we have this as an axiom in Peano arithmetic? Any idea?
Because it's inductively proved.
Yeah, there's a very simple proof by induction of this, and it's not even a very interesting case by induction because the sort of success you've only got 2 interesting cases in the sense rather than a whole infinity of interesting cases. But anyway, so this is provable in Peano arithmetic, but we need to have it in Q in order for Q to have enough principles to be able to work with them. We'll see why that is fairly soon in this lecture. Okay, so we've got Q here. It actually turns out there are some interesting theories between Q, a lot of interesting theories between Q and Peano arithmetic, which, given that we have the tools to define them, then I might as well do that now. So a very important one is what's called I sigma 1. And this is it's the same axiomatization as Peano Arithmetic, but include the induction axiom only for sigma 1 formulas A. Okay, so we don't have induction for arbitrary formulas with arbitrary nestings of quantifiers, but we do have the sigma 1 formulas. So those are existential quantifiers plus some bounded quantifiers. Restrict induction to delta zero formulas, and that suffices to prove some things. And people also do things like they consider, so people are very fascinated in what goes on in between, what goes on with weak theories of arithmetic and their connections to fields such as computational complexity. Another one people often consider is I delta zero together with the statement that says the exponential function exists. The exponential function is definable in the language, representable in the language. So we have a formula that represents it, but if you only have I delta zero, you can't prove for all x and y there exists a z such that z is the exponential x to the power of y, if you only have delta zero induction. I delta zero adds that axiom. If you've got sigma 1 induction, you can prove it anyway. Yeah, just to say doesn't really matter what this is. I mean, this isn't going, I delta zero plus x is not going to play much of a role in any role in this course. I just wanted to mention it. So here we have induction. Will play a big role when we come to Gödel's second incompleteness theorem. Okay. And one interesting thing about I sigma 1, it's again 6 axioms plus an induction schema. You have the induction for all sigma 1 formulas. But in this case, unlike Peano Arithmetic, it is finitely axiomatizable. So Peano Arithmetic is not finitely axiomatizable. You can prove there is no finite axiomatization. I sigma 1 is finitely axiomatizable because you can find a few finite universal instances of the induction principle for sigma 1 formulas. And these are actually related to the existence of the universal Turing machine. There's that connection. But I'm not going to go into that in more detail. Right, so now we've got Q. I can state today's main theorem, which is basically Gödel's first incompleteness theorem, but not in the form that Gödel first stated it, and the proof is not going to be the same style of proof that Gödel gave. It's a much shorter proof in a sense, but less informative. So our main theorem is we have some theory T which is consistent and computably axiomatizable extension of Q. So all the theorems of Q are theorems of this theory. Then T as a theory is incomplete. So remember, Number consistency means that false is not in the theory. So actually, if T is a theory, because theories are closed under deduction, we could just say false is not a sentence in T. But I'm going to, it's quite standard in logic when you're talking about axiomatic theories to a little bit blur the distinction between the axioms and the theory. So if we think of a theory closed under consequence, then if T is closed under consequence, then we can definitely say that. But if we put it in this form, then we allow T to be just the axioms as well. So it's kind of, this is the standard way of writing it. False is not a consequence of T. Notice also that instead of using the entailment relation, the one with the semantic turnstile, I'm using the proof theoretic one. Of course, they're equivalent by the soundness and completeness theorems that we've proved. And once again, when one's in the context of working with axiomatizations, and so we're somehow interested in what we can prove from the axioms, it's standard to use the proof theoretic relation here for the notation. So now consistency will be written in as this, and completeness is then for every sentence A, we can either prove A or its negation. For every sentence A. So these were in very early lectures, but just to remind you, either we can prove A or we can prove the negation of A. Okay, so from this theorem, it's clear that Peano arithmetic is not the same as true arithmetic, is a proper subset of true arithmetic, because true arithmetic is the theory of one model, of a single model. So true arithmetic is necessarily consistent and complete because it's the theory of a single model. Peano arithmetic, we believe, well, we know it's consistent because it has a model. But we'll come back to how we really know it's consistent in a couple of lectures' time.
So the statement of completeness correct?
Oh, yeah. No, it's not. Yes. Sorry. Thank you. So the Peano arithmetic is consistent. It's computably axiomatizable, as we've discussed. It's an extension of Q because by induction you can prove the Q axiom from Peano axioms. So therefore, Peano arithmetic is incomplete and therefore does not coincide with true arithmetic. Okay. So this would be the goal theorem for today. Only I'm going to simplify it very slightly. Okay, you'll see. You'll get this extension in the exercise class either next week or the week after. So the actual theorem we're going to prove here. The actual theorem we're going to prove is we're going to strengthen consistent to a property called one consistent. Okay. What one consistent means so one consistent makes sense. These consistency and completeness are properties that hold for any logical they don't hold for any logical theory, but they're properties that make sense for any logical theory. One consistency makes sense only for logical theories about numbers, well, in the language of arithmetic, logical theories in the language of arithmetic. And this says for every sigma 1 sentence, say, then A is true in the natural numbers. So we can't prove any false existential statements about numbers. So existential statements, any false statements of the form, there exists some numbers such that then a decidable property involving only bounded quantifiers holds. Okay? And it's clear that this implies consistency because false is trivially a sigma 1 sentence. And if t proved false, then false would have to be true in the natural numbers, and of course it is. So t doesn't prove false. Okay, so I think that's. I mean, I started late, but still, this is a good stopping point because we have the main theorem we're going to prove. Are there any questions before the break? That's from my cable. Okay, so the goal is to prove this theorem. Maybe just another word about this one consistency, which may seem a bit of a funny assumption here. Even with that, it's still a pretty good theorem. So we're trying to axiomatize the truths of arithmetic. If we axiomatize the truths of arithmetic, we certainly want the theorems that we can prove from our axiomatization to be true. And one consistency is only requiring that, not even for all the theorems we proved, but just for the sigma 1 sentences. So for those existential statements about decidable properties. So it's really a very weak assumption on the theory. This is going to rely on two crucial ingredients. The first one is going to be what we're going to spend most of the time proving, and it's the first one is something called sigma 1 completeness of the theory Q. And the second property is to do with being able to encode computability theory in the theory. Now, I know not everyone in this room has done a course on computability theory, so that part I'm just going to say what's needed from computability theory. And in any case, that ingredient is not going to be crucial because next week when we move on to Gödel's proof, we won't need the computability theory in the background. Well, not in the way that we need it today. Okay, so the main step is going to be this, the result that I called sigma 1 completeness. So let's state that as a theorem. So actually, sigma 1 completeness of the theory Q. And what it is the converse to inconsistency. If you have a sigma 1 sentence, if it's true, then Q can prove it's true. The Q is a very weak theory. It doesn't have any induction. And actually, how weak it is, you're going to see in the exercise class next week. So, for example, in Peano Arithmetic, you can, of course, prove that addition and multiplication are commutative and associative, and there are proofs by induction, and you need proofs by induction to prove those. In the theory Q, you can't prove that that addition and multiplication are commutative and associative. And actually, one simple, if I'm right that the ordinals are a model, that already proves that you can't prove the commutativity of addition and multiplication. But you'll consider other models next week in the exercise class. So sigma 1 completeness says that any sigma 1 sentence, A, if A is the truth of arithmetic, then A is provable in the theory Q. So we don't need any induction. So Q may be a very weak theory, but for existential properties, it's not weak. It can prove everything. But that, just from the fact it can prove all those sigma 1 properties, you might think, oh, that's amazing. But actually, as soon as you start thinking about really what it means, it's not so amazing, because the sigma 1 property is of the form, there exists k different numbers such that some delta 0 property holds of those k different numbers. The delta 0 property is expressed entirely in terms of bounded quantification. So once you've put actual numbers in, it reduces to basically conjunctions and finite numbers of conjunctions and disjunctions. And then you're essentially just proving a number of equalities between expressions involving addition and multiplication in numbers. So actually, it's not such a striking result, although it's an important result. I'm going to do the proof in quite a bit of detail so that you get some experience of how one deals with formal theories. And you will get more experience in the exercise class next week. Some of you that have done courses on theorem proving and proof assistance and this kind of thing, you have anyway some experience of doing things with formal theories. Right, so for sigma 1 completeness, we need a number of steps. I'm going to publish the handwritten notes. So we'll see, I'm going to start going through them painstakingly, and then at some point we might decide to bail out and just take some things for given. So the lemmas are lettered, and the first one to build up to show that Q can prove any true sigma 1 sentence, we're going to build up from simpler sentences. So we're going to just start with atomic formulas, which is equalities, and we're talking about sentences. So we've just got equalities between closed terms, and closed terms are built out of, well, successors not very interesting. So essentially addition and multiplication. So lemma A is going to deal with those. So lemma A says that Q can prove if you've got two numbers, M and N, you consider the term that's the addition of the two numerals, then it can prove that that's equal to the numeral for the sum of the two numbers. But I've already basically discussed how that works when I introduced axioms A3 and A4. We discussed how that works. You basically just says the number, you take n rewrite steps to pull the successors from the numeral for n out to the outside, and you get the numeral for n plus n. A3 and A4 using axioms A5 and A6. You have a similar statement for if you've got a product of two numerals, then that can be proved to be equal to the numeral of the product.
Excuse me, you would presumably use metalogical induction to do this.
Aha, yeah. So this is for all numbers m and n in the natural numbers, but this universal quantification is in the metalogic, and we're just proving a particular sentence for each m and n. We're proving a particular sentence or two particular sentences in the actual logic in Q. Yeah, so it is indeed by induction in the metalogic. Induction on n in both cases. Right. So lemma B is the workhorse of proof. Let's write it up here. So lemma B says, again, for all numbers n, so meta-theoretic quantification, Q proves the sentence all x if x is less than or equal to the numeral of n. Well, that holds if and only if the disjunction holds. But if and only if x equals 0 or x equals the numeral for 1 or x equals all the way up to x equals n. And because it's an externally universally quantified thing, I'm just going to omit the universal quantifier, but we're talking about the sentence, proving a sentence here. Okay. Occasion over a natural number. And notice now the shape of the sentence itself depends on that number. So how long the formula is, the length of the sentence with the universal quantifier is linear in the number n that we've taken. And it's clear that this should be true, and the point is that Q can prove it. And it's actually, oops, bless you. It's actually a little bit complicated to prove this. So, this is the one I really want to do in detail. So the proof. Well, so firstly, a point to make. How does one prove that Q proves something? So one thing we could do, we have the axioms. One thing we could do is we have our Hilbert system. We can give proofs in the Hilbert system. We could show for any number n, we can find a proof in the Hilbert system from the axioms. So that would be a very, very painful way of doing things. Because we've got the soundness and completeness theorem, all we really need to show is that this if and only if follows as a logical consequence of the axioms. Okay, so that's what we're going to do. This is the sort of thing that if one is formalizing a proof, which later on we shall need to actually not just do this proof, but formalize it, then it becomes painful because you actually have to do if you're formalizing the proof, you don't have the semantic convenience of reasoning about logical consequence, and you have to go back to the formal Hilbert proof system. But anyway, we're going to do it. We're going to show that from the axioms of Q, each of these sides of the if and only if implies the other as logical consequences of the axioms. So we'll do the left to right, the right to left implication first. So to show Q proves the right to left implication. So that's what we're showing. But this is the first time I've ever done this. I've noticed when having oral exams in Slovenia, this convention that if you're going to show something, you state it and then you put dashed lines underneath. I don't think I'd ever seen this before coming to Slovenia, and it's taken me 10 years to actually dare to do it myself. But now, do you learn this at school? Or high school?
No, we learn this here.
Uh-huh.
Yeah, the faculty.
Okay, all right. Anyway, well, I didn't know it until I got it. So now, this is the first time I'm using it. So we're proving the right to left implication. So we're showing that a disjunction implies a conclusion. So we just need to show each disjunct implies the conclusion. So for each m less than or equal to n, meta-theoretic, we need to show that m is less than or equal to the numeral for m is less than or equal to the numeral for n. But Now we just expand the definition of less than equals. So i.e., so this direction is easy, but let's do it. So we need to show, so we're needing to show that Q proves that there exists a Y such that M plus Y equals N. But we can do this because we can just use the meta-theoretic operation of subtraction to consider the number n minus n. And we have that Q proves M plus quality, because this is one of lemma A. And let me just say as required, because if a property holds for a specific term, then certainly the existentially quantified property holds, and therefore this holds. So I've kind of done it by backward reasoning, but we did it. So that was the easy direction. Okay. I was going to say the more interesting direction. I'm not sure interesting is the right word, but the more involved direction is the other implication. And it is really quite involved, surprisingly so. The right implication. So we're going to use meta-theoretic induction on the number n. Okay. So we don't have induction in Q, but we have meta-theoretic induction, of course. This case here. In the case that n is 0, so I'm just going to go, this time I'm just going to end up with this implication, which one, sorry, the left to right implication as the conclusion in a number of stages. So we're going to start with, we have in Q that x is less than or equal to 0 implies there exists a y such that x plus y equals 0, because that's just the blue. So this is just the definition of less than equals. So as the next step, we use the Q axiom, the special axiom that we'd added for Q, and this is the main place in the this and also in the step case of the induction. This is why we needed this principle. So remember, the Q axiom said for any x, either x equals 0 or is the successor of some y. So this y here that exists is either 0 or the successor of some z. So Q proves that if x is less than or equal to 0, then either x plus 0 equals 0, or z such that x plus s of z is that x plus the successor of z equals 0. And this is again the definition of less than equals. Okay.
Excuse me.
Yep.
Is it by definition or the last axiom of the?
Sorry, this is by axiom of Q. Thank you. Yeah. Okay, so now we use. Oh, I didn't need Q proofs twice. Q said, yeah, never mind. So now we use the axiom 4. So
Should it say x equals 0, not x plus 0 equals 0 on the left side of the disjunct?
Well,
It is right.
we've instantiated for y that the y is either 0. So, I mean, of course, the next step, we're going to make this express.
Oh, I see.
Yeah, but this is because we expanded y as either 0 or the successor of z in the axiom of q. Yeah, I know I'm doing it one step at a time, but I'm now going to do 2 steps because I'm going to use the 2 axioms for addition in parallel. So x is less than or equal to 0 implies either x equals 0 or there exists a z such that the successor of x plus z equals 0. So here we're using A3 plus A4. And now the successor of anything is never 0 by axiom 2. So this case is ruled out. So we have Q proves S is less than or equal to 0 implies X equals 0. And that's what we needed. So we're done. Row case. Let's do the successor case on the right. So we're going to, for the successor case, I'm going to assume for n and prove for n plus 1. So the induction hypothesis is going to be exactly this left to right implication as written here. The induction hypothesis, let's put it in blue to separate it from the rest of the proof. So if x is less than or equal to the numeral for n, then either x equals 0 or it's one of those numbers between 0 and n. And we need to show, well, we need to show the same thing for n plus 1 here. So again, I'm just going to do it in a number of steps. So we have that Q proves x. We've got x is less than or equal to the numeral for n plus 1. Then, well, now using the axiom of Q on x, either x is 0 or x is the successor of some y. So we have, there exists a y. Oh no, sorry. Sorry, we're going to expand out the less than equals again. So there exists a y such that x plus y equals the numeral for n plus 1. Again, that's the definition of less than or equals. So following on from that, we have, so now we're going to again apply the Q axiom to y. So like we did before. So if x is less than or equal to the numeral for x plus 1, then there exists a z such that x plus 0 equals n plus 1, or let's do it like this. X plus 0 equals n plus 1, or there exists a z such that x plus the successor of z equals n plus 1. Equals the successor of n. Because the successor of the numeral for n, because that's the numeral for n plus 1. Okay, so here we've again applied the axiom for Q. And yeah. Okay. So once again, we can do the computation with the plus in both the 0 and successor case. So we have that x is less than or equal to n plus 1. The numeral implies that either x equals the numeral for n plus 1, or there exists a z such that the successor of x plus z equals the successor of the numeral for n. So here we've used, again, A3 and A4.
Excuse me.
Yeah.
You may be in writing S n. There also use the lemma A.
This was just the definition of the numeral for n plus 1 is s applied to the numeral for n.
Yes, of course.
Yeah. So it was just expanding the definition. Okay, and now we apply axiom 1 that said that successor is injective, so we get x plus z equals n. Yeah, so or and so this is A1. But I'm going to do 2 steps at once. So we recognize this as the definition of x being less than or equal to n. Okay, so let's just put that in here. So now this is saying x is less than or equal to the numeral for n. So I've now used A1 and less than equals in a single step here. And now we use the induction hypothesis, which gave us this implication, and we see that we get to where we want. So then finally, Q proves that if x is less than or equal to n plus 1, then, well, this disjunction or this, so indeed x equals 0, or x equals 1, or x equals n, or x equals n plus 1. And we're done. Oh.
Wouldn't you have a shorter proof if we did the first 3 steps and then did induction?
The first 3 steps.
Because they're exactly the same, both for the 0 and for the.
Oh, I see. Probably, yes. Yeah. Exercise. Yes. I don't want to shorten it now, but that's a good thought. Yes. So. I kind of like the idea it should be long and nasty. Right. So once we've got this, we've got lemma B now. So we have lemma C and lemma. Let's do the whole thing. I mean, is it okay for you to? I mean, you've got a holiday tomorrow. You can sleep it off or something. So I lack a good idea of how to shorten the next lemma, which and it is a little bit important because it gives us the reason for considering the previous lemma, so to speak. Because lemma C is clearly a step in the right, whereas what we've just done, it might not be clear what it's good for. Lemma C is clearly a step in the right direction. In fact, it gets us most of the way because lemma C says that if we have a delta 0 formula, not sentence, so let's give it k free variables is delta 0, then for all numbers that we can use to instantiate the k free variables, we have the implication that if A is true, equals n1 to nk in, for the numbers n1 to nk, then Q proves A with nk. Okay. So for delta zero formulas, for any particular instantiation that's true, Q can prove it. And this we now prove by induction. So this is a very long proof because it's by induction on the structure of the formula. And we can build formulas using the propositional connectives, using atomic formulas, the propositional connectives and the bounded quantifiers. So that the bounded quantifiers are unsurprisingly the interesting case. So let's do the case of one of the quantifiers. So proof, so by induction on the structure, we break the formula down, we prove it for the smaller parts of the formula, and then you show that if it applies to the smaller parts, it applies to the formula as a whole. So by induction on the structure of the formula A, and we consider the case that A is a bounded quantifier. So for all x less than or equal to t, B holds. So here, we'll assume that B has free variables x1 to xk and also x. Okay? And then the formula A has free variables x1 to xk. And notice the condition that Gregor pointed out last week, which was important, that when we have a bounded quantifier x, so here the free variable, the variables in t are at most x1 to xk. Okay. Right. So we want to prove this implication. Is true. So for all x less than or equal to t, B one up to nk. We instantiate with some numbers n1 up to nk. And we need to show that Q proves this. The numerical value of t instantiated with, where x1 to xk are instantiated with n1 to nk. Okay, we just calculated the number there, which is easy because the term just consists of additions and multiplications and successors. Natural numbers, then it's true that for all x is less than or equal to n, B holds of that B holds for n1 to nk with 0, and so all instantiations of B holds. Where are M. Okay. So it holds for all x's less than or equal to m, so in particular it holds for 0, 1, 2, up to m, and that's always true. So implying the induction hypothesis, these are all structurally smaller formulas. When we look at the structure of the formula, we don't look at the term structure, we look just at the logical structure of the connectives. So these are structurally smaller formulas. So by the induction hypothesis for each of these cases, by the induction hypothesis, we have that Q proves B with the numbers n1 to nk 0 in, and Q proves this as well. So all n plus 1 of those formulas, from 0 up to n. And then so hopefully some of you can already see how we're going to use lemma B in order to, we want to prove that Q proves this bounded quantification here. But of course, if Q proves all of these, then just by properties of disjunction in first order logic, Q proves that the disjunction disjunction, well, for all x, if x equals 0 or x equals 1 all the way up to x equals m, then D holds for n1 up to nk for x. Okay, that basically follows immediately from these k plus 1 assumptions there. And now we use the lemma B because this disjunction is equivalent to saying that x is less than or equal to m in Q. Q could prove, lemma B said that this disjunction is equivalent to statement x is less than or equal to Q. So Q proves for all x is less than or equal to m implies the numerals here, n1, nk, x. By lemma B. But by lemma A, Q proves that n equals T of n1 to nk. It's not quite by lemma A. Lemma A was about one addition and one multiplication, but if you proved it from addition and multiplication, it's trivial for successor, as we already discussed. So it holds for all terms. So actually, lemma A would have been better stated for all open terms. Any closed any instantiation with numerals can be proven equal to its value. That would have been the best statement of lemma A. But anyway, essentially by lemma A, so I'll try and remember this for next year. But anyway, essentially by lemma A, we have for all x is less than or equal to t, implies d n1 nk x. Aha. Well, that we can, because we're substituting, we need to substitute n1 for nk. Let's do it in 2 steps. So let's substitute n1 up to nk here. Implies d of n1 nk x. And that's the same thing as for all x is less than or equal to t, implies d x1 to xk x, where at this point we're substituting the n1 to nk remaining three variables, which are x1 through to xk. And this is exactly for all x less than equal to t, boundary quantification for all x less than equal to tb. So this is exactly a n1 up to nk. Okay. Good. Well, so we're nearly there. I would like to keep the statement of lemma C. So I shall just rub off the bottom half here. And finally, we can prove sigma 1 completeness, and it's now very easy. So proof of sigma 1 completeness. So consider any sigma 1 formula. So that's going to be it should be sigma 1 sentence. That's of the form, so remember a sigma 1 sentence is a finite number of unbounded existential quantifiers followed by an A that of course might contain those three variables where A is a delta zero formula. And suppose this sentence is true. So suppose it's true in the natural numbers that there exists an x1 up to xk such that A holds. I just write A. So because this is true in the natural numbers, there of course exist natural numbers, real natural numbers in the real world, x1 to n1 to nk, for which A is true. So let n1 to nk be such that A of n1 up to nk is true. And then by lemma C, Q proves A with the numerals for n1 to nk instantiated. And then just in first order logic, if you can prove some instantiation of an existential formula with terms, well then the rules for the proof rule for, we didn't actually have a proof rule for existential quantification because we were dealing with this Hilbert system where we just had a universal quantification and we were defining existential quantification. But anyway, if we did have one, it would be such a proof rule that you can prove an instantiation and you can prove the existential quantification. But in any case, I said we don't need to reduce it to the primitive proof steps. Obviously, if A is true for some instances, then it's a consequence of that the existential statement is true. So, because it's a logical consequence, Q proves there exists x1 to xk such that A holds. And we're done. And we have spent a whole hour of the lecture proving sigma 1 completeness. Right, so the remaining work to be done is relatively small, but I still think we should have a break. And then it'll be a short, maybe, is it okay to have a 10-minute break? So we'll have a 10-minute break and then a short third hour, or probably an hour. So we have the sigma 1 completeness of Q, and therefore we also have sigma 1 completeness for any extension of Q, because obviously if sigma 1 sentence is true, is provable in Q, so it's obviously provable in an extension of Q. Extension just means you have more theorems. So we have that every extension of Q is sigma 1 complete. And we want to show that every consistent, computably axiomatizable sorry, not consistent, I mean, this is true, that's true, but we're going to show for every one consistent, computably axiomatizable extension of Q, the theory is incomplete. Okay. And we're going to get this via a second theorem, and this is going to be, so the first theorem, the incompleteness theorem, we'll call theorem A. We're going to get it via theorem B, which is if T is a one consistent extension of Q, without any computably axiomatizable assumption, then T is undecidable. So there is no algorithm that tells us if a sentence is a consequence of T or not. And theorem A follows from that. So theorem A is that if you're a complete, consistent, if you're a, sorry, not complete, because we're going to be incomplete, if you're a one consistent, computably axiomatizable extension of Q, then you're incomplete. Can anyone see what the link is between theorem A and theorem B? It's something we did 2 weeks ago. The model theory, decidability by model theory. So theorem A follows because of let me just remind you then, Janicek's theorem said that if you have a complete, computably axiomatizable theory, then you're decidable. Every complete, computably axiomatizable theory is decidable. Okay, so we're going to get incompleteness as a consequence of undecidability. So as I've already said, this was not how Gödel first got his theorem, and in many ways it's less informative, this method, than the method that Gödel followed. So we'll do Gödel's proof next week. In fact, when Gödel proved his theorem in 1931, and the very notion of undecidability wasn't introduced, decidability and undecidability wasn't introduced until 1936. And the undecidability of arithmetic was essentially established by Gödel and, sorry, not Gödel, by Turing and Church in 1936. And then this approach to incompleteness became available. Right, so this was in lecture 10. This Janicek's theorem, so we don't need that. So actually, our remaining goal is to prove theorem B, and then we're done. Right, so to prove theorem B, we need a bit of computability theory. And for those who don't know computability theory, who don't have much background in computability theory, that's okay. You can take what you can from what follows, but in any case, next week we're going to do Gödel's approach to his theorem, and we're not going to require so much computability theory. But to approach this, we're going to remember from last week's exercise class the primitive recursive functions. Gregor did do the, sorry, not you, Gregor, but Gregor Dolinard, the assistant, did do the exercise class, did do the primitive recursive functions last week. Yeah, good. So I'm going to use a theorem, which I mentioned last week, even though I haven't covered the primitive recursive function. The primitive recursive functions, well, let's put it, well, anyway, I'll write it like this, but it's better in the notes. Every primitive recursive function is sigma 1 representable. Are sigma 1 representable, are all sigma 1 representable. So last week we showed this in a particular case of the exponentiation function. So I already mentioned that the proof basically generalizes to primitive recursive functions, and I'm going to leave that as something that, if you want to see more details of that, look in Rautenberg's textbook. And then we're going to borrow a result from computability theory. And we're going to, and that's this, which is, it's not in the form that you would see proposition in a computability theory textbook, but if you know computability theory, this is a simple result. So from computability theory, and this is, there exists a binary, so a 2-argument primitive recursive function n, for which there exists an m such that Tmn equals 0 is undecidable. So primitive recursive functions are computable functions. Given any pair of numbers, we can compute t of mn and see if the value is 0 or not. But here we're considering the set of those numbers for which there exists some m such that Tm of n equals 0. And this is a typical thing that you can semi-decide, in that you can, if a number's in here, you can verify that it's in here by computing t of 0n, t of 1n, t of 2 of n, and waiting until you find the right number for which it's 0. And the problem is you never know, if there doesn't exist such an m, you never know when to stop the search. And in fact, the existence of an undecidable, of a primitive recursive function for which this set is undecidable, is saying that in general it's impossible to tell when to stop the search. Okay, so we're just going to take this as a fact, and but just for those of you who know some computability theory, I mean, you should just be able to see this is true, but a specific example for those who know computability theory is, e.g., take t of x, y to be 0 if capital T of x, x, y, where this is clean as capital T predicate, and 1 otherwise. So I could start going into explaining what this capital T function means and things like that, but I think I'm just going to leave it at this. You can, this is a black box that we're borrowing for those of you who don't know computability theory. Okay, so now we can prove theorem B. So we'll just remember the statement, which I'm going to rub off. So we need to prove that if we've got a one consistent extension of Q, then we're undecidable. Okay.
Excuse me.
Yeah.
Should like big T maybe be 0, then equals 0. Maybe.
Now this is a predicate.
Oh,
But maybe I don't remember. I don't remember how I introduced it in
I
the,
don't remember this.
in the
It
Yeah.
was supposed to equal 0.
Yeah.
Okay, well, it's
That's-
yeah. This may not be consistent with my computability theory notes from the computability theory course, but one often thinks of this as just a predicate. It's either true or false. Anyway, never mind. Let's not nitpick on that. So the proof of theorem B. So let T be a one consistent extension of Q, and we need to prove that it's undecidable. So one consistent extension Q. So we'll suppose for contradiction that it's decidable. This means the contradiction that T is decidable. So we're going to prove that we can decide this undecidable set. We can then decide, let's call this U, that undecidable set. We can then decide so deciding a set means we produce an algorithm which, given a number as input, will return yes if n is in U and no if n is not in U. So the algorithm is input n that there exists a y such that g of little t of number, the numeral for n, y 0. Otherwise, where g of t here, this is the sigma 1 formula that represents the primitive recursive function little t. The sigma 1 formula representing t, which is a formula with 3 free variables because t is because it's representing a binary function, and these are here 0 is the result variable and y are the are in the two argument positions. And this is correct, right? So we're basically saying, can we prove in T this exists a y, there exists, I've swapped the arguments here, haven't I? It should be y n here. Because here we're saying there exists an n in the first argument. Yeah. So that's a mistake in the handwritten notes that I shall publish on the course webpage, but probably with the mistake in because yeah, I don't have time to correct them right now. Right. So this is saying basically there exists a y such that little t of y n equals 0. And this is correct. This is correct because it holds that T proves there exists a Y GT Y n 0 if and only if n belongs to U. And why does that hold? What about this direction? So if n belongs to U, that means there exists an m such that little t m n equals 0. Holds by sigma 1 completeness because this is a sigma 1 formula that states that property. It's true and therefore it's provable in Q and therefore provable in T. So this implication holds by sigma 1 completeness, which is why we need sigma 1 completeness. And this implication holds because of
plus the definition of representability.
well, we're taking the definition of representability, so I was meaning something else. So we want, it's a sigma 1 property, we want, if it's provable in the theory T, it's true. That's exactly one consistency, right? So this implication is one consistency. That's why we need one consistency in the proof. But one consistency can be eliminated by a clever argument that turns the existential quantification into a cleverly bounded quantification in a certain way that will be done to trick you due to Rosser, and that will be done in one of the exercise classes, but I'm not sure whether next week or the week after. Right, okay, so we've proved theorem B and hence theorem A. Just to end with a remark, which is, so we've proved that any nice, one consistent, computably axiomatizable extension of Q is incomplete. For example, Peano Arithmetic is incomplete. Peano Arithmetic is one consistent because all the axioms are true in the natural numbers, so in fact, everything you can prove in Peano Arithmetic is true in the natural numbers. So the fact that Peano Arithmetic is incomplete means that there are formulas that are sentences that are true in the numbers that are not consequences of the axioms of Peano Arithmetic. By soundness and completeness of first order logic, not consequences can be interpreted as either we don't have a proof, but it can also be interpreted as there are models of the axioms of Peano Arithmetic in which these true sentences about numbers don't hold. So one of the consequences of Gödel's incompleteness of the first incompleteness theorem is that there exists some very strange models of the axioms of Peano Arithmetic, models in which true properties of numbers don't hold. We already know that there exist some other exotic models of the axioms of Peano Arithmetic, because in a previous lecture we had what was it called? The elementary
Countable elementary extension.
Right, the elementary extension theorem. Thank you. That said that because the natural numbers is infinite, there is a proper elementary extension of the natural numbers, and that proper elementary extension is a different countable. There's even a countable one, a different countable structure that models the axioms of Peano Arithmetic. Structure from natural numbers, but the thing that's different there is that's an exotic model of the axioms of Peano Arithmetic in which the true sentences are still exactly the same as the true sentences of true arithmetic. So one doesn't change the truths of arithmetic. So by Gödel's incompleteness theorem, there are also exotic models of Peano arithmetic that change the truth of some arithmetic sentences. And in the 1970s, people like to play with these exotic models, and they use them to find the first example of, so we've got some, that there are some statements you can't prove in Peano that are neither provable nor refutable from the axioms of Peano arithmetic. And the example we've got here is, well, anyway, that's not, we'll get to a very good explicit example next week. But anyway, you get funny examples relating to the undecidability of certain sets and things like that. They're not natural mathematical statements. So it was considered a very nice result in the mid 1970s when I use it by playing with these exotic models of Peano arithmetic. Some logicians found a variant of Ramsey's theorem that is a theorem in the language of arithmetic, but is not provable in Peano arithmetic. So that was the first example of an apparently natural mathematical statement. It's not actually Ramsey's theorem. Ramsey's theorem is provable in Peano arithmetic, but a variant of Ramsey's theorem is not provable in Peano arithmetic. And this result was originally obtained by playing with these exotic models. Good. Well, I think that's enough for this week. I wish you lepe praznike, and yeah, have a nice weekend, and see you next week. Are there any questions before we finish? Okay, good.